In this lecture, we continue with vectors. So this is part 2 of vectors. In the first part, we talked about definition of vectors. We talked about the definition of vectors, how we represent a vector. So, for example, vector x is equal to x elements, x sub 1, x sub 2, and x sub n. We talked about vector equality. So when vector x is equal to vector y, it means their dimensions are equal. And for all I from 1 to n, which is the dimension, xi is equal to y sub I. We also talked about how we can represent vectors, what's the dimension of vector, which is the number of elements in that vector. We also talked about specific types of vectors, such as zeros, ones, and unit vectors. In this part, we are going to continue talking about more details of vectors. All right. So vector addition and scalar multiplication. The goal of this part is to understand the following concepts and see some examples of each concept. First, we are going to talk about vector additions, how we can sum up two vectors. Then we talk about the properties that vector addition has. Next part is geometric representation of vector addition. Then we talk about scalar vector multiplication. What will happen if we multiply scalar alpha to vector x? We then talk about properties of scalar vector multiplication, and finally we represent the geometric representation of scalar vector multiplication. So as you can see, it has both a theoretical component and also a visualization component. Then you want to see what's the geometric representation of each of these concepts, both for addition and scalar multiplication. All right, vector addition. Let's assume vectors A and B are two given vectors with the same dimension. If dimension of A is not equal to dimension of B, in that case, we cannot have addition defined for these two vectors. So this is the required condition to be able to sum up two vectors. To add two vectors, we simply take the sum of A sub I and B sub I. What does that mean? Let's say dimension of A is equal to dimension of B is equal to n. So for I from 1 to n, what we do, we say A sub I plus B sub I. And let's call this C sub I. So sum of these two vectors, so A is A1, A sub 2, A sub n. B is B sub 1, B sub 2, B sub n. So the summation vector A plus B is equal to A sub I plus B sub I, A sub 1 plus B sub 1, 2 plus B2, and A sub n plus B sub n. We call them C sub 1, C sub 2, and C sub n. We can call this vector C. So sum of two vectors is also a vector. Let's look at an example. What this example tells us is we have vector A is equal to 1, 3, 5. We have vector B is equal to 2, 4, 6. So as you can see, dimension of both these vectors is equal to 3. So we can sum up these two vectors. Then we want to find out the elements of the summation vector. So 1 plus 2 is 3. So this is A sub 1 plus B sub 1. 3 plus 4 is 7. And 5 plus 6 is 11. Let me talk about one more example. Vector A is equal to 1 and 2. vector B is equal to -5, 6, 4. So what is summation of A and B? The answer is this doesn't exist. What is the reason? Because dimension of A is 2, dimension of B is 3. So 3 is not equal to 2, so we cannot find the addition of these two vectors. We cannot sum up these two vectors. So where this is going to be useful in real world scenarios, let's say you have two vectors that you are storing the amount of data which is stored on two different computers. For example, let's call one of them computer 1. So it has 10 gigabytes of data, and these are at each of the times. So this is at day 1, and this is at day number 2. And at the second day, there is 125 gigabytes of data stored on computer 1. And then you have computer 2. So at day 1, computer 2 stored 0 gigabyte of data. Probably we had less data. But at day 2, there is at day 2, there is 182 gigabytes of data. So if you want to see collectively how much data we have stored in a network of computers, we just need to sum up C1 and C2, which means 10, 125 plus 0, 182. So the result of this summation, which is 10 plus 0, 125 plus 182, this is going to be the total data that we stored in day 1 and in day 2. All right, next. We want to talk about some properties of vector addition. The first property is it's commutative. What does that mean? It means if you change the location of them, it doesn't affect the result. Let's look at an example to make sure this makes better sense. Let's say A is equal to -2, 4. B is equal to 1, 0. So A plus B is going to be -2 plus 1, 4 plus 0, which is -1, 4. And B plus A is 1 minus 2, 0 plus 4, which is equal to -1, 4. So as you can see, these two are equal. So this is the commutative feature. And if you want to prove this in general, you just need to define vector A to be A sub 1, A sub 2, A sub n, and vector B to be B sub 1, B sub 2, B sub n. And at the end of the day, what's going to happen? We first find out A plus B. A plus B is equal to A1, A sub 2, A sub n, plus B sub 1, B sub 2, B sub n, which is equal to A sub 1 plus B sub 1, A sub 2 plus B sub 2, and A sub n plus B sub n. All right. So before we proceed further, I want to remind you one more important point. As you can see, the assumed dimension of these two vectors is the same. All right. Now we use the commutative feature, the commutative property for scalar summation. What does that mean? That means A1 plus B1 is equal to B1 plus A1. The same for other rows. And Bn plus An. So now I try to decouple this into two vectors. B1 to Bn plus A1 to An. So what is this? This is B, this is A. B plus A. So our proof is completed. A plus B is equal to B plus A. So these are not going to be the questions in the exam or like the homeworks. This is just to give you an idea of how we can prove each of these statements, each of these properties. So I did it for the commutative. You can do it for associative and other features as well. All right. So the associative feature tells us if you have three vectors A, B, and C with the same dimension, let's say their dimension is n, then A plus B in parentheses plus C is equal to A, vector A plus the summation of B and C. This is the associative law. The next one is the zero component. So if you sum up any vector of dimension n plus the zero vector with dimension n is equal to the same vector. So vector A plus vector 0 is equal to vector 0 plus vector A is equal to vector A. And another thing is, if we deduct any vector from itself, the result is going to be 0. So A subtract A is equal to 0 of dimension n, assuming that the dimension of vector A is also n. Now we want to look at the geometric representation of vector addition. So as we talked about, let's call the addition of vectors A and B to be vector C. So now we want to show them in the two-dimensional space. What does that mean? That means vector A has two elements, two components, and vector B has two components, and vector C, which is their summation, also has two components. So adding the vectors is equivalent to moving a point from the origin, A1 plus 1 units on the x-axis, and A sub 2 plus B sub 2 units on the y-axis. Let's take a closer look at an example. So we have vector A, which is 4 and 2. So what we want to do, the first element is x-axis, the second element is y-axis, right? So vector A is 4 and 2. 4, this is A1, and 2, this is A2. This is A1, this is A2. We have the same for B. B sub 1 is 1. So this is B sub 1, and B sub 2 is 3. So now we want to see what's the geometric representation of their summation. So A plus B is going to be 4 plus 1, 2 plus 3, which is equal to 5 and 5. Let's look at this axis. This is 5, C1. This is also 5, C2. So this is the geometric representation of adding two vectors in the two-dimensional space. So if we have 3 dimensions, then we are going to deal with something like this: X, Y, Z. And then your vectors are going to be in the n-dimensional space. So that's not, I think, let's do this. Then your vector is going to be something in the n-dimensional space. Let's say this is vector A, and then we start drawing vector B from the end of vector A. This is vector B. So vector C is going to be, let me choose another color. This is going to be vector C, which is A plus B. So we start vector A from the origin, then vector B from the end of vector A, and then vector C is from the start of vector A to the end of vector B. This is in the 3-dimensional space. This can go to further dimensions, but we can illustrate them on this 2D space, I would say. All right. Next is scalar vector multiplication. So to multiply a scalar alpha and the vector x, we multiply each component of the vector let's say xi, we call the components of that vector by x sub I by alpha. So vector x is x sub 1, x sub 2, x sub n, and then we have alpha. So alpha x is alpha x sub 1, alpha x sub 2, alpha x sub n. Let's take a look at two examples. First example, 3, scalar 3 multiplied by vector x. So 3 multiplied by 1 and 5 is equal to 3 multiplied by 1, 3 multiplied by 5 is equal to 350. Another example is -2 multiplied by the vector 3, 2, 7. So we multiply it by each of the components. -6, -4, -14. And two specific examples that I would like to talk about. One is 0, scalar 0 multiplied by any vector is going to be vector 0. And scalar 1 multiplied by vector x is going to be vector x. So if you multiply any vector by a scalar 1, it's going to be the same vector. If you multiply it by 0, scalar 0 is going to be the 0 vector. All right. So the properties of a scalar vector multiplication. For the following properties, let's alpha and beta be scalars and let x and y to be n-dimensional vectors. So we have two scalars, alpha and beta are scalars. We have vectors with dimension equal to n. All right. First of all, it's commutative. So for vector x, alpha beta, which is an scalar multiplied by vector x, is equal to alpha multiplied by beta x. The second property is left distributive. What does that mean? Alpha plus beta x is equal to alpha x plus beta x. Next one is right distributive. So x multiplied by alpha plus beta is alpha x plus beta x. Another property which is not listed here is when you want to multiply a scalar alpha to summation of vectors x and y, this you can distribute alpha to the parentheses. So it's alpha x plus alpha y. So assuming that vectors x and y have the same dimension, you can multiply alpha to both x and y. All right. So a scalar vector multiplication, as we went over this example. All right. A geometric representation of a scalar vector multiplication. So the first example, let alpha equal to 2 be a scalar and x be a two-dimensional vector. The product of alpha x has the effect of stretching the vector to its twice length. So we have x, let's say x is equal to 0 and 4. So the length of x is 4. And then we want to find 2x. 2x is equal to 0 and 8. 8. So it stretches the vector to twice its length. And then let's alpha be minus 0.5, be a scalar, and x be a two-dimensional vector. The product of alpha x has the effect of shrinking the vector to half of its length to the reversing direction. So in our example, minus 0.5x is equal to 0 minus 2. So x was 4 towards the positive direction, minus 0.5x is minus 2, or is 2 towards the negative direction, to the reversing direction. That can happen in other directions as well. So if this is vector x, this is going to be vector minus x minus 0.5x and 2x. Right, next. In the next part, we are going to talk about transpose. For now, let's wrap up the addition and multiplication of vectors here. So in this lecture, we talked about two vectors. Let's say to have two vectors x and y. Dimension of x is equal to dimension of y is equal to n. We also assume that we have, so these are vectors. We have alpha and beta, which are scalars. First, we talked about vector addition. So if these two vectors are equal, then we can define vector z equal to x plus y, where each element of z is sum of the corresponding elements from these two vectors. Also, we talked about scalar vector multiplication, which is alpha multiplied by x. Let's call this z. Then zi is equal to alpha x sub I for I from 1 to n. We also talked about the properties of vector addition and scalar vector multiplication, as well as their geometric representation.